Hi, in this video we're going to look at the gradient of the curve y is equal to x squared. We've just got the positive part drawn here. So this is a curve y is equal to x squared for positive values of x. So when x is 2, y will be 4. If we look at the other point here, when x is 3, y will be 9. Now, if we want to find the gradient of the curve at any point, then the definition of a gradient of a curve is to draw the tangent. So here we have the tangent drawn at P. If we can now calculate the gradient of that line, which is in fact 4, okay, we can find the gradient of the curve at that particular point. Now the problem is, of course, the gradient as we move around the curve changes, so we need to find some sort of formula. So given that y is equal to x squared, can we actually find a formula for finding the gradient of the curve at a particular point? So when we've got the formula, we take our value of 2, we can put it into our formula and get a value for the gradient. This is what we're going to do. Now, one way to do that is to so if I wanted to find the gradient there, is to pick another point close to P, so I'm going to call that point Q, and then draw a chord like that. Okay, and then what happens is we move that closer to it, and you can see what happens. The chord and the tangent, the smaller that this value gets of d delta x, which is what we call it, they will coincide. But let's go back to the original point and just remove the tangent for the moment. Okay, so we've got the point P where we're trying to find the gradient. Okay, we take another point Q, and what we say, if the coordinate of P is x, then the x coordinate of Q will be x plus a little bit of x, we can say, or x plus, and the name uses delta x, but you can think of it as x plus a little bit of x. Now the y coordinate of P is going to be x squared. Okay, but the y coordinate of this point Q is going to be x plus a little bit of x all squared. And now to find the gradient of a line, we do this distance divided by this distance. So we can think of that as a little bit of y divided by a little bit of x. So let's just click here to see what I mean by that. So I've got a little bit of y divided by a little bit of x is qn divided by pn. Now that distance there is given by that distance there, so it's going to be x plus a little bit of x, or x plus delta x minus x squared, and this distance here, okay, is going to be x plus a little bit of x, or x plus delta x minus x plus delta x minus x. That will give me the gradient of the line. Okay, if I expand x plus delta x, I'm going to get x squared, 2 lots of x delta x, plus delta x squared, and I've still got to take away that x squared at the end. If I do x minus x here, I just get rid of a little bit of x. Okay, on the top here, the x squared minus the x squared will cancel out, and therefore I get 2x, this bit in the middle here, plus a delta x squared over delta x. If I factorize out a delta x, which I can do, at the top I'm going to get 2x plus delta x, at the bottom I've got delta x. Now provided delta x is not equal to 0, I can cancel that out, and then I get that 2x plus delta x. Right, now what happens is, of course, is I move this point here, and it will coincide with the tangent, and will become the gradient, okay? But what I must make sure I do is not let it be equal to 0. So what I do is I move it very, 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 very close to it, but not actually equal to 0. That's probably about as close as I can get it. And you can see down here, the gradient here is going to be at 4. It will become equal to 4, which is actually the gradient at that point. And what we're going to consider is that the gradient will be, the function, the formula will be 2x plus that little bit of x. But that little bit of x is so small that we can actually ignore it, and we will just say that the gradient will be 2x. Okay, and when x is equal to 2, if I put x is equal to 2, 2 times 2 does actually give me 4. Now, I can actually show you this. Let's try this. So, if I turn this on and this on, what it says here in the table is when delta x is 1. So, when this distance here is 1, the gradient, i.e. that distance divided by that distance, will be 5. And what I do is I make that delta x become very small, and I can do that by moving the slider. Now this, and it'll start recording the results, okay? So what happens, I'll start recording the results, and recording the results, okay? And it's still recording. Okay, at 0 it won't work, okay? So let's just go back a bit, so it's 0.9, and then we'll just do it with the arrow keys. What you can see is the value is getting smaller and smaller. I went past it, okay, but it went smaller and smaller. It's getting smaller and smaller. Here at 0.01, it's tending towards the number 4. And if we approach it from the other side, which you can do, if you go from the other side, so moving from the other side, moving towards that point again, it's getting 3.9999, and then actually at 0 it won't actually be a value. So if we just take it there for a moment and then move the arrow key, that way you can see it will approach, get very close to 4. That's about as much as we can get, 3.99. So we can say at that actually particular point, although we can't divide by delta x, the gradient is equal to 4. However, what we've discovered here is that when y is equal to x squared, the gradient function is 2x. And this process is called differentiation by first principles. You won't have to do it in an exam for IGCSE. Maybe for A level you would have to. But what we're saying here is the gradient would be equal to 2x. Okay, so I have put the notes, this GeoGebra App, the link, I will put it in. Unfortunately, on the web version, this bit here, the recording, doesn't appear to work. So you can always try and download it for yourself and then open it up in GeoGebra, and maybe it will actually work, so it can actually record. Okay, so this has been a video to show you how to find the gradient function of the curve y is equal to x squared by first principles. There is, in fact, a much easier formula for doing it, which we'll look at next. I hope you've understood, and I thank you very much for watching.